Here we have a different sort of resonance tube. The turbulence in the air as the tube goes through the air creates a standing wave pattern inside the tube. If I go faster, I can get a higher harmonic. And higher. And we can play taps. Alright, I've got my two tuning forks with the resonance boxes. I have a couple of quarters taped over here. So this one is a little lower than this one. Let's play them together. Can you hear a little warbling action? Because they're not exactly in tune, they drift in and out of phase, getting louder and quieter, louder and quieter. Each time they get louder and quieter, we call that a beat. Now I have the tuning forks going into the speaker, acting like a microphone. And we're going to see what it looks like on the oscilloscope. You can see my voice a little, can't you? That's the one tone. There's the other. Now we'll play them together. You can see the amplitude is warbling. That's the waves drifting in and out of phase. We can use the superposition principle to explain what's going on with beats. I've set it up so we can see one wave, and now the identical wave right on top of the first one. The sum shows up below. The amplitude is bigger. Now I have the same first wave, but look at the second wave. It's 180 degrees out of phase. What are they going to add up to? That's right, 0. We're now going to have 11 Hertz versus 10 Hertz. Both starting at the same phase angle. First wave, second wave. Notice how they're in phase at the beginning, but then they drift out of phase. Then they drift back in phase. That's how we get loud, quiet, loud again. Going from loud to quiet to loud is one cycle. That's one beat. The difference is 1 Hertz. We're going to go to 12 Hertz. First wave, second wave. Now you can see that they're drifting in and out of phase more rapidly. The difference is 2 cycles per second, and that's the frequency of the beats. Well, eventually, if you get them to be too far apart, you don't really see a beat pattern here.